So you can hear me, yeah? Good. So I'm going to talk about primarily distributed deep learning, actually. And we'll do distributed TensorFlow and a bit about our platform at the end. So I introduced this diagram yesterday. I find it conceptually a useful way to understand how to build an AI company. You need to handle data at the bottom. Typically, we will have data engineers who work on this kind of level. And if you can manage data, you can build reliable data pipelines to bring data into your organization to collect it, typically in data lakes. You can have data science team who can then work on that data. So that'll be nice, clean data. Maybe they can use it for training deep learning models. And if you're really lucky, you have a lot of GPUs and a lot of compute, you can do things like distributed deep learning, which currently is, you can see it as being at the top of the pyramid of the AI hierarchy of needs. And people like Google, Facebook, and Baidu do this routinely. And then the type of people who do that, you might think, well, are they data scientists? Would I trust my Python people to do that? Or do I need data engineers? So I just call them data science engineers. Really, they're data scientists. And I kind of see data scientists being able to spread on this pipeline. They're not stuck in the middle forever. And I said I was going to talk about distributed deep learning. Surprisingly, when I come here, I have to explain to people why I think GPUs are important, right? So that kind of surprises me a little bit because all the advances we've had in the last 5 years has been really deep learning and GPU driven. I'm going to go a bit through about how distribution is important to help us improve the state of the art of deep learning. So we're always interested in building better prediction models, lower generalization errors. And there's 3 points I'll cover. One is how do we get larger data sets? And I'll talk about that first. And then how do we scale compute? In this case, it's GPUs. And how can we use that scalable compute to find better model architectures? So many of you will have seen this diagram before, or some variant of it. I think Andrew Ng popularized it before. Basically, it said that if I have a small amount of labeled data, maybe existing traditional machine learning models can outperform deep neural networks. But as the volume of data quality, good quality training data increases, I can get better prediction performance, lower generalization error from deep neural networks over traditional ML. So what's interesting about this is that Baidu had a paper, and the paper came out just a few weeks ago. I linked earlier on to a blog entry by Adrian Collier who describes the paper. But they basically quantify how much labeled data I need to get an improvement in prediction performance. So this is the graph. You can see it's actually a log-log scale. So it's a straight line on a log-log scale. It's a power law relationship. And basically what it's saying is if I get into this region in the middle, this part here, so now I've enough training data that I'm in this region. Well, now I know how much more training data I need to get an improvement in my prediction performance. So we can see that a little bit. This is taken from Adrian's blog. But you can see here that as a company, you can say, well, if I collect this much more training data, I can expect this return on my investment. You probably see this implicitly a lot when you hear about the number of hours that Tesla have driven in their cars. Yeah, you'll say, well, we've gone 2 million. And in their head, they have some number. Yeah? They're saying, well, we want to get to 2 million gets us here, and 10 million hours of driving gets us here, and we'd like to get down to the irreducible error region. So as a business, then, you can invest in collecting that data because this power law relationship that Baidu found in their paper, they found it in many different fields. They found it in image classification, in voice recognition, in machine translation, and in voice synthesis. So across all these different fields, they saw the same improvement in prediction performance based on larger data sets available. Now, you may be smart and say, well, come on, I'm going to do a better model. What happens if I design a better model? I don't need as much data. And that is true. But what it will do is it will shift the axis down. So we see that red line is the better model. So that basically means if I can design a better model, I will get better prediction performance for the same amount of data, but somewhere that line is going to stop. And then the angle of the slope will still stay the same. It's not going to change, right? So at some point, to get better prediction performance, you're going to have to increase your data set volumes. So that's data as the so that's why I kind of talk about this from a big data perspective. Big data I see as being central to building better predictive models. The next point is compute. What will compute get me? Maybe I can train models faster. compute is now used at many of these hyperscale AI companies to get us better models. So the founder of reinforcement learning, Rich Sutton, he basically came out recently, I saw in a talk of his, he said, well, methods that scale with compute are the future of AI. This is the guy who did single agent reinforcement learning, right? And he's telling us that, no, you want to go distributed. And what can we say about the current world and methods that scale with compute? Well, the state of the art machine or deep learning models for doing prediction in CFAR10 and ImageNet, they're two image classification data sets. They're very well known. And they're both recently, this is a paper from early March, it was using what we call model architecture search. So what's going to happen is you're going to run lots of experiments in parallel on lots of different GPUs, and each one is going to have a slightly different model architecture. Maybe there'll be an extra layer on one, maybe there'll be a skip connection, maybe we'll change the learning rate. There'll be small variation on all of these. When we run lots of these in parallel, we can then use methods like evolutionary algorithms to pick the best models. And then in the next iteration, we generate new models based on those particular models. And the state of the art was actually using a technique, a genetic algorithms technique that picked it kicked out actually the oldest models, not just the best. It wasn't just a fitness function picking the best. It was also kicking out older models. So they use a lot of compute to do that. You can see they said 450 GPUs over 7 days. That's quite a lot. TPUs a bit more. And the improvement you got over another model based on reinforcement learning wasn't huge, but it was a bit. Okay. But if you're at the higher end, if you're working in finance and a slightly better predictive model gives you a competitive advantage, then maybe this investment is good for you. And the same goes for self-driving cars and so on. But lots of GPUs and parallel experiments are not just used to find better models, to do model architecture search. We typically do this for hyperparameter optimization. Now, if you're just working with a UI-driven tool and you're doing a simple random forest model, you're still going to have some hyperparameter search. You might do some cross-validation. This is a natural thing you do. But when you come into the deep learning world, people just tend to forget that and go, well, screw that. No validation set. This is too big. I can't do it. Right? But that's not how people work at the hyperscale AI companies. The reason why we don't think about it is because you have maybe 1 or 4 GPUs on your desktop, and you say, well, the time to do that model architecture search will be way too long. The time to try out all of these hyperparameters, that'll take me weeks. I can't spend that time. This is the outer loop of not training, but the outer loop of finding good hyperparameters. So this is plug number 1. So if you have a platform like Hops, or if you're working in a managed cloud service and you have access to lots and lots of GPUs, you will do this because you will get better models out of it. So then the next thing that comes into our pyramid or hierarchy is if you're going to go and use parallel GPUs, you will need a distributed file system underneath all of this. You'll need it for storing the training and test data and sharing that between, if you're doing data parallel training, your evaluation results, your configurations, your hyperparameters. If you're running TensorFlow, you need TensorBoard to aggregate the logs. Distributed file systems are also important for managing larger data sets. So if you want to read in a very large data set from a single machine, you may not have the capacity for that. If you're doing training with TensorFlow, you'll want to do model checkpointing and hyperparameter search and model architecture search I've mentioned already. So the option comes then where you say, OK, I need a distributed file system. What am I going to pick? I'm leaving out the obvious ones like NFS. So scalable distributed file systems are things like HDFS, our own HopsFS, which is HDFS compatible. And you have MapOr and Chef and Ceph and GlusterFS. These are quite well known. If you go to the cloud, you'll have object stores like S3, GCS, and Windows have their own file system. I wrote these are slow, right? Because if you're going to take your data set like ImageNet and copy it into S3 and then try and write a simple program to train with it, you're going to be I/O bound. Your GPUs will sit there idle and just wait. Because S3, you're going to set up a HTTP connection. It's going to have to establish that, and then it'll read. And it'll read at quite low bandwidth. So the reads bandwidth you get in S3 might be 10, 20 megabytes per second, which is not very much. But it's the latency that will kill you. Just to give you an idea of where we are, this is plug number 2. In our particular file system, HopsFS, we put small files in the database. So for a real-world data set, 9 million images, it's a bigger version of ImageNet. With the same hardware, we can outperform HDFS by whatever, 4.5x for reading images. So that's basically so file systems are not all created equally, and do your homework on them. I think what most people associate with distributed deep learning is the training. So you kind of think, I have bought a lot of GPUs, or I have access to a lot of GPUs on Amazon or Google. My training performance should get faster. And you kind of, in your head, you might have an idea of a graph that looks something like this, that it might not be quite linear reduction in training time based on the amount of available compute, but it'll be pretty good. So what the goal of distributed training, of course, is that if you have a large data set and it's taking a long time to train it, it could be up to weeks, that you can get that down to a very small amount of time. And the hyperscale AI companies, they do this naturally, and it doesn't phase them at all. And the time to train ImageNet, if you do it on one GPU, it'll be on the order of 2 weeks. So Google recently presented results where they did it in 22 minutes. The real big one was last year. Facebook actually showed they did it in 1 hour, and they did it on P100 NVIDIA GPUs. And this got a lot of coverage, in the last year, because people kind of suspected, I think, that, hang on, if I was working at Facebook, I wouldn't be sitting here for a week waiting for a model to train. I'd be doing this in an hour. And then kind of they came out and said this, and people said, oh, okay. And this was followed by a lot of other companies started being more open about the kind of GPU infrastructures they have internally. That's kind of what you would expect. The thing is that in practice, and I'm a distributed systems person as well, that in theory it should scale linearly, but in practice it doesn't always. Particularly I think people get burnt mostly when they go straight in and try and run with distributed TensorFlow. So distributed TensorFlow doesn't scale, and it's not, I don't think anybody is really using it in production. And when I talk about distributed training, implicitly everybody now talks about synchronous stochastic gradient descent. So a few years ago, a lot of people were doing the asynchronous variant of this called Hogwild. But there was a very influential paper by Google just a year and a half ago at ICLR where they basically showed for them that we can get better accuracy with distributed synchronous SGD than asynchronous. So there's no real advantage to going with the asynchronous model. So everything I talk about will be distributed synchronous SGD. So this is where I get back to this issue of the dogs around the bowls. Right? If you're going to go with the Google distributed TensorFlow model, you'll be using the bottom thing called parameter servers. And what this diagram is basically saying to you is that it won't scale. Yeah? And this is what you'll see in practice. In fact, the line will go down. Right? So as you add available compute, it'll actually get slower for larger models. So the state of the art, the current state of the art that people are doing to beat the ImageNet results is an algorithm called AllReduce. And I'll just show you what AllReduce is visually. I won't go through the actual algorithm. I think somebody's presented it earlier in the conference. Firstly, we start with the parameter server model. If you look at the blue box, that's our parameter server, and you can have more than one of them. But in principle, what's happening is on every iteration of SGD, you will read in a batch, and the batch will be split up. So each GPU will read in a different set of training examples from that batch. They'll all compute their gradients. They'll send their grade. Oh, we're going on the left one, sorry. On the left one, you can see that we're doing Ring-AllReduce first, I remember. So in Ring-AllReduce, it's the same thing. Each GPU is reading in different rows from the same batch, and they compute their gradients, but they send them on the ring. They send them to their neighbors, and they receive gradients from their neighbors. And after a full reduction phase, they gather the results from their neighbors, and they'll all can update their model locally. So every GPU will have a full copy of the model. And that's what you have in data parallel synchronous stochastic SGD. So the same is true in the parameter server model. Each GPU has a full copy of the model. They send the gradients to the parameter server. It either sends back diffs to them, but typically a whole new model gets sent back. And if your model is quite big, and you have 256 GPUs and your model is 100 megabytes, you can see that even with a high-end InfiniBand network with 112 gigabits per second, it's still going to take a long time to send that data back. So typically you want a very large batch sizes here. And Facebook had a batch size of 8,000 in their experiments there. And they introduced actually a learning rule for how to train with that large batch size. So you can read up in the paper. So the lesson here is that network bandwidth is actually the bottleneck for distributed training. And if you want to actually do distributed training, you should use an algorithm like AllReduce. And as I'm Irish, the cliche, you can say the gradients flow better in AllReduce, and you have a nice bottleneck on the parameter server there. And that is a Guinness, and I will be having one this evening. Okay, it is Friday. Just to give you an idea of you show me the numbers, show me the money. This is vendor, but it's not really vendor. It's actually Uber who presented these results, and they compared AllReduce and distributed TensorFlow, the parameter server model, and for Inception and ResNet, they look not too bad, but when you get to a larger model, VGG is a larger model, has more parameters, and that means there's more network bandwidth required. You can see that for 64 GPUs, distributed TensorFlow got slower. It was only 70% of the throughput. But the Horovod, which is their implementation of AllReduce, that got a 40x improvement in training, a reduction in training time, 40x. So the lesson here is if you have bigger model, parameter servers don't scale. Network bandwidth will ultimately be your bottleneck. The corollary there is you need the infrastructure for it, right? So no one is doing these type of experiments on the public cloud, right? You would need InfiniBand, dedicated InfiniBand network. And typically, it's all being done on-premise right now. I think Microsoft actually in Azure, they have introduced InfiniBand, so it may move that way in the near term. But right now, the new results are all being generated on-prem. Okay. Taking a step away, so what does this mean in code? Show me the money. I'm a Python person. I don't trust all of this stuff. Show me this in context. So what I've been talking about is distributed deep learning, but that doesn't exist in isolation. Everyone knows that a lot of the work you need to do is you need to build up pipelines. And pipelines will take data, they'll ingest it from some place, they're going to transform it, you're going to have to verify, you have to label feature extraction, and we have to do our experimentation and training and testing and verification of the models and before we finally can get to the serving part. And what we can kind of see right now, at least in the TensorFlow world, is that there is a kind of a convergence on typically the ETL stuff will be done in Spark if it's big data. So organizations who have large amounts of data won't be doing their ETL necessarily in TensorFlow. It won't scale. But the TensorFlow is used a lot, either Keras or TensorFlow on top of TensorFlow for experimentation and training. And then serving right now, you don't really have much else if you're training models in TensorFlow than TensorFlow serving itself. So to do this, you'll need to have some infrastructure, either on cloud or on-prem. Typically, Kafka as a message queue would be a normal way of ingesting data. And then you'll need something, resource manager, Mesos, Yarn, Kubernetes, and you'll need a distributed file system. So TensorFlow serving typically will be done on Docker containers in Kubernetes. Now, this is where we get back to our pyramid. Right now, people are kind of divvying up their teams into, we have the data engineering team who do the data extraction and analysis, and then we have a data science team, and then we have an ops team for managing these and monitoring these models as they run in production. And this is kind of scary for smaller organizations. You're kind of going, I can't do all of this. This is too much. So this is not the way we look at it in our company, Logical Clock. So on our platform, Hops, if you have small data, you can do all of the data prep in TensorFlow if you want, and just do TensorFlow serving. And you don't necessarily need to be a data engineer to do that. You can be just a data scientist. I'll show an example later. And we don't see it as being different teams doing different parts of the pipeline. We see it as being one project, one team who's responsible for the entire pipeline the whole way. And if it needs a data scientist and a data engineer, fine, so be it. If it just needs a data scientist or a few data scientists and one data engineer, fine. You find the right team for that particular pipeline. If it's big data you're working with, you're not going to use TensorFlow on its own. You're going to use something like Spark. It could be Scala Spark or it could be PySpark if you want to stay Python the whole way, and that's OK. And our platform has pretty much the same components that I mentioned earlier, like Kafka, the HDFS, Spark, and TensorFlow and Kubernetes. Well, Kubernetes is actually work in progress, I should say. Some of you who are looking at this are going, yeah, this is fine. I'm going to go kubeflow anyway. Right? And kubeflow is fine. You can use Kubernetes. The reason why we think our platform has some advantages over going with the Kubernetes model is there's some operational reasons. Firstly, there's no integrated enterprise security framework for Kubernetes. So you will say Istio, but Istio doesn't give you end-to-end with Spark and encryption in transit for everything, and there's no encryption at rest. Stateful services, you'll still need them anyway. You'll still need your distributed file system. You still need to run etcd, Kafka, databases. No one is running these in production on Kubernetes right now. And then from a data scientist perspective, if I want to run on our platform, well, I just need to install Python libraries from the UI. But in Kubernetes, you'll need to write YAML files to change how many GPUs you're going to use. You'll need to maybe write a new Docker file to install a new Python library. And then when you want to run a pipeline, you have to do the whole startup time. It's going to be very slow. So we have this as stateful data in the cluster. So let's have a look at the code for this, just to give you not to scare you off. If you want to do data prep with just TensorFlow, many of you will have heard of the dataset API. It's now in core. And this is just reading some images from an image directory on the first line files. And then you have a function which will take a batch of those files and return them as a data set. And then you can do the read function, the parser function, which will do your data prep. So anything you need to do to modify your data, you can do that. And then there's some other optimizations in there because you don't want to run this single-threaded, right? And TensorFlow has some support for doing this multi-threaded and buffering data so that you'll get some performance out of it. But remember, this is going to run on a single machine. So what if I have bigger data I don't want to run on a single machine? I have a cluster. Well, most people will use PySpark or Spark in Scala to do this. And a lot of things that you may think are normal, right? You say, well, I'm data science. I don't want the whole data set. Give me just 10% of it. Well, it's lost me. Then you just put in the sample ratio, the amount you want, right? So this is a new API in Spark 2.3, the images API. And you just get a smaller sample of the data. You don't have to do much work. This code is actually more Pythonic than the TensorFlow code. It's easier to read and easier to write. And here we're just resizing some images and cropping them. And the thing is that this thing will scale, right? So this can run on hundreds of machines and go orders of magnitude faster. We have our own way of doing hyperparameter optimization if you have lots of GPUs. So if you want to train your models on tens of GPUs, if you want to, in this case, if you want to do hyperparameter optimization, you'll maybe want to have different learning rates and dropout rates. So here you can see we have 6 different combinations of learning rates and dropout rates. So if I call the bottom function experiment.launch, it will call this model function above and pass in our args_dict. And it will actually start 6 different executors in Spark, and each of them will run the TensorFlow code we put in there. So typically then what will happen at the end is they'll write the results to HDFS, and then TensorBoard will aggregate it, and you'll see which ones worked best. So which combination of hyperparameters gave you the best prediction performance. I'll do an example of that later on. What it looks like, just to give you a feel for it, is you can see this kind of thing in your TensorBoard, and then you can visually inspect which combinations gave you a lower error rate. Distributed training is interesting. It's what you can do in Horovod is the platform we support. We also support TensorflowOnSpark, but that's the parameter server model. Horovod requires very little changes to your code in TensorFlow. You basically need to wrap your optimizer in this HVD distributed optimizer. In our case, if we want to launch the job, we do it from a separate notebook, and that's because Horovod runs with MPI run, which we kind of run underneath Yarn. But it doesn't make it too difficult. So if you want to just put normal TensorFlow code, you have a chief in Horovod, which will typically do model checkpointing and so on. But then the rest of the code will just be dumped in those if and else statements. The API is bigger than this. We have our own API for managing TensorBoard using HDFS. And we have another one for model architecture search with genetic algorithms. And there's other ways of making it easier to read and write from Kafka and so on. If you want to do model serving, then we have a REST API, but you can also use the UI just to pick your model, press serve, and then you get at the endpoint of the model, and you can use gRPC to then make calls directly on the TensorFlow model server. Okay, we're out of time. Okay, so I'll just with this I kind of covered the last time, so we'll skip through it, and I have 25 minutes here, but okay, we're good. So I went through this the last day, so I'll skip over that. Yeah, you can do Python per project. This is all integrated in the platform. I have a video. You can, if you want to have a demo of this, you just talk to me, I can go through it with you. It's online. And yeah, just to summarize, a quote from Andrej Karpathy, this is basically the way things are going. Deep learning workflows will be distributed, they will be auto-tuned, and even the schedules at which they run will be auto-tuned. So that's it, and that's our team.
Thank you very much, Jim.
Okay.
Any questions for Jim? Oh, yeah, right.
Another Irishman here. So thanks for the talk, but what do you feel in terms of like specialist APIs for like machine learning, like, you know, in general? Like, so you've done all this kind of work with your company. Do you see this as like an inevitable thing that will, like, you know, companies like Facebook and stuff will build themselves, or like, you know, how do you feel in terms of like, you know, the gap between what people are saying, oh, TensorFlow can do this, and all the other work you have to do on top of that?
Yeah, that's a tough question. I mean, we know what the hyperscale AI companies are doing right now, and they're doing extremely impressive things. I think it's more a question of what can other people do to catch up, you know? Yeah, and you know, you can go on cloud and you can pay for Google's managed TensorFlow service, and it's quite good. If you're stuck on-prem, you can talk to us. But ultimately, I think, you know, just my feeling here is that people haven't even got up to GPUs yet. And you really need to start, if you're going to be doing deep learning, you need to be working with GPUs primarily. And once you start doing that, then you'll see naturally that, hey, if I have 10 GPUs, I can you know, do my experimentation 8 times faster. And you'll just work that way. I mean, the question about what APIs and so on, we think TensorFlow is one of the dominant platforms, so we support that primarily. Keras will be very big. It is already. The rest of them need to catch up, you know.